We're looking at lesson 5 here, comparing two proportions using a hypothesis test. So last time we compared two proportions using a confidence interval, and if you'll recall, our way of doing that was looking at this model p1 hat minus p2 hat, had a sample of p1 minus p2, and had a standard deviation of square root pq over n for the first group, and pq over n for the second group. And the way that we compared two groups is we looked at the sign of the difference. So if we notice that P1 minus P2 was bigger than 0, this is equivalent to saying that P1 was bigger than P2. If we saw that P1 minus P2 was a negative number, was less than 0, this was equivalent to saying that P1 was less than P2. And finally, if we had 0 inside of our confidence interval, that told us P1 minus P2 could be equal to 0. We said the results were inconclusive. The reason why we said the results were inconclusive is this means that P1 could have been P2. So to compare two groups, we look at the difference of those two proportions. Today we're going to use the 4 steps of the hypothesis test, so just as a quick reminder of what those steps are. Step 1, we state our hypotheses. This always looks like our parameters, p, mu, or sigma, equaling some given number. Our alternative hypothesis is either less than, greater, or not equal to that given number. Second step is model and assumptions. Model, we're using the model from last time, model that we studied a bit ago there. This has several assumptions to it. Reminder of what those assumptions are. I need to make sure that I'm sampling with no bias, so I call that the random sample check. I need to make sure that one sample does not affect another within the group that it's in. So that's independence within. The backup for independence within is called the 10% rule. And I also need to make sure that one sample doesn't affect a different sample from different groups. I need to have independence between groups. And finally, I need large N, so I need to have at least 10 successes and 10 failures. When I'm saying these assumptions, you should really be thinking this is for each group. So first step, hypothesis. Second step, model. Third step, p-value. Fourth step, conclusion. So that third step, the p-value, let's look at that definition again. Definition of p-value is this is the likelihood of the sample data, or more extreme, if the null hypothesis is true. So if you'll recall in the past, what I've done for hypothesis tests is I've taken whatever number is in that null hypothesis and I plug it in for my p when I've been creating the model. I'm going to do the same thing here today. Whatever I'm assuming in that null hypothesis, I'm going to be plugging that in as a foundation for coming up with my model. And then I will use my sample to come up with the value when I'm finding that z-score. You can probably hear my cat here in the background. As a fourth step, conclusion. If your p-value is low, if your p-value is less than your alpha, you're going to reject the null hypothesis. If you reject the null hypothesis, this means you have evidence of an alternative. If your p-value is large, you're going to fail to reject. It's kind of like staying in place. If you fail to reject, you don't have evidence of that alternative hypothesis. So let's look at an example of this thing from start to finish. And this is one of those days where we actually kind of have most of the pieces already to just get straight into it. We're not going to have to do a ton of theory. There'll be one tiny trick, but let's look at that trick when it comes up. So suppose that Tim Drake has enjoyed spending most of spring along the waterfront. After several weeks of casual observation, he notices that a higher percentage of individuals tend to go inner tubing in the evening compared to in the morning. So we're going to test if the proportion of people that go in the evening is higher than the proportion that go in the morning. So to do this, he samples, randomly samples, so it's telling us we meet one of those assumptions, several summer days, and attends the river sometimes in the morning, sometimes in the evening, but never both. So this way I don't have one person affecting another. This is telling me I have independent groups. He finds that 60 out of 140 individuals go in the morning, and 50 150 out of 260 go inner tubing in the evening. So first step says state the hypotheses. I'm going to have both a null and an alternative here. So reminder, null hypothesis, this is telling me that there's no difference between the two groups, that there's no change. Null means no. Alternative hypothesis is telling me that there's some difference between the two groups. So I'm going to see if I can come up with these things. And I'm actually going to write them two different ways. So you can start out writing it the way that I'm writing it, and then with time you can shift it over to the second style. So first way I'm going to write this is the probability of the evening group is the same as the probability of the morning group. Here's what I mean by this. For the null hypothesis, I'm always going to have an equal sign, and it represents there being no difference between the two groups. In other words, it's back at this kind of setup here. I'm assuming my first group is equal to my second group. Alternative hypothesis, I'm going to find this by reading the paragraph, notices higher percentage in the evening than the morning. So what Tim Drake thinks is that this evening proportion is larger than the morning proportion. This is a totally acceptable way of setting this up. In fact, this is telling us our direction. So notice here, this is pointed to the right. When I draw my normal distribution, I'm going to have a right tail shaded in. Now, I just want to write this a tiny bit different because if you'll recall, previously we've always had a number on the right side. And when I look down here, I'm not seeing a number on the right side, I'm seeing a symbol. So here's my plan. I'm just going to take this PM and I'm going to subtract it to the other side. So if I subtract that over, I'll have the probability of the first group minus the second group, evening minus morning, is equal to 0. I've moved that over. If this looks familiar, this is the same way I was checking those confidence intervals for conclusion. If 0 is inside of my interval, it tells me the two groups could be the same. For the alternative hypothesis, I have evening minus morning. I'm moving the symbol to the other side, is greater than 0. So if I have a positive number, that tells me the first group is larger than the second group, that the evening group is greater than the morning group there. We're going to see that it's advantageous to actually have these things written down both ways. So when I turn the page here, I'm going to write down my pair of hypotheses. In practice, once I do these things, I tend to write either one. The second set is way more common. So first step, I have my hypotheses. I'm going to write down those hypotheses again. My null hypothesis, evening is equal to the morning group. Alternative hypothesis, the evening group is larger than the morning group. And another equivalent way of writing these same things. Evening group minus the morning group is equal to 0. There's no functional difference between the two groups. Alternative hypothesis, evening minus morning is greater than 0. So first step, hypotheses. Second step, model. Third step, p-value. Fourth step, conclusion. I have my hypotheses. I'm going to try to come up with my model. Reminder, my model is success rate for the first group minus success rate for the second group. We've already decided that we're going to do evening minus morning here. It is normally distributed with the center of evening minus morning for the population success rates. Evening, morning. Now the good part is if I get evening and morning switched up here when I'm writing down this standard deviation, it won't really matter. It's going to give me the same value if I write these down in this different order, because addition is really forgiving in that way. 3 plus 5 is the same thing as 5 plus 3. So usually this gives me a number like equals 30%, and I plug 30% in for all of those numbers. That's how I form my model. I don't quite have that here. It doesn't say that the evening number is 70% and the morning number is 50%. So it doesn't give me numbers like it normally gives me numbers, but it does give me something a little bit different. This is assuming the null hypothesis is true. If the null hypothesis is true, this tells me that the first group success rate is the same as the second group success rate. So in other words, it doesn't matter if I'm looking at the evening group or the morning group, the percentage that go inner tubing for both should roughly be the same. So what this means is, if I'm looking at this model here, my evening group and my morning group, this should be the same number. So for example, if this is 50%, this should also be 50%. And 50 minus 50 is 0. If this is 20 and this is 20, 20 minus 20 is also 0. So when I'm setting up the model, and I'm skipping ahead a little bit here, and I'm looking at evening minus the morning, the null hypothesis says this first group and the second group look the same. So if I'm taking the same number and I'm subtracting it, I should end up with an anticipated no difference between those two groups. So I'm halfway done with my model already. Finding z-scores is going to be really easy, because when I'm subtracting the center this time, I'm going to be subtracting the number 0. Let's go back to the formula for the model and look at some other ramifications though. I'm going to plug the same number in for P here that I plug in for here. I'm going to plug in the same number for Q that I plug in here and that I plug in here. Small problem. I do not have values for the first success rate or that second success rate. It doesn't give me population values. It gives me sample values. I can figure out that 60 out of 140 for the morning and 150 out of 260 for the evening. I could find the sample rates, but it doesn't say it's claimed that 50% go in the morning and 20% go in the evening. So what do I know then? Well, if the first group is the same as the second group, then I'm assuming the evening rate is the same as the morning rate is the same as the overall success rate. Here's what I mean by this. I think that it's not really one group compared to a second group. I'm claiming I think these two groups look the same. So for all intents and purposes, this should just be one mondo big group. And the name of this group is going to be a pooled success rate. Here's how a pooled success rate works. When you say there is 60 successes in the first group and 150 for the second group, I'm not really hearing 60 for the first and 150 for the second. I'm just hearing the total number of successes. In this case, I'm just hearing 210 successes. When I'm looking at the total number that this is out of, I don't think it's out of 140 or 260 people. I only see one group. I see that this is out of the total of these things out of 400 individuals. So my pool success rate, I'm taking the total number of successes and I'm dividing this by the total number of trials. Okay. So let's find that pooled success rate together here. I'm going to take the total number of successes for the first group. I'm going to add the number of successes for the second group. Number of trials, I'm going to take the number of trials for the first group and I'm going to add the number of trials for the second group. 60 for the first, 150 for the second, 140 for the first, I have 260 for the second. So what I'm doing here is I'm taking the two groups and I'm combining them. Earlier, when I was trying to find two different success rates, I was never going to be able to do that because really what's going on is I'm assuming that there's just one success rate. So everywhere where I have the success rate for the first group, I'm going to be plugging in this pooled success rate. Everywhere where I have the success rate for the second group, I am also going to be plugging in this pooled success rate. This is super strange the first time you do it, but as you practice this, it will get a lot smoother. So we're going to do a couple of examples of this. So far, I have 210 people went inner tubing out of 400 people that went to the river. That tells me that 52.5% of people went inner tubing. If that's my success rate, then the pooled failure rate, this is everyone that did not go inner tubing. So if 210 people did, well, that means everyone that's left over, 190. I got 190 by doing 400 take away the 210. It's everything that's left over. This tells me that 47.5% of people do not go inner tubing, regardless of whether that's in the morning or evening, because I'm pretty much pretending that I can't tell time here, that it's one big group that I'm combining together. If you do 1 minus P, if you're looking at this, it is still giving you your value for Q. So when I'm coming up with my model, I'm going to have the first rate minus the second rate, but I'm pretending they're the same number. That gave me a center of 0. When I'm setting up the standard deviation here, I'm going to have P and Q, where this P and Q is the P'd and Q'd success rate. I'm going to have P and Q, not for the first group, not for the second, but the combined groups. I'm assuming it's one big setup here. Divided by the number of samples in the first group, divided by the number of samples in the second group. So I'm going to have a big standard deviation here. First success rate, 52.5%. First failure rate, 47.5%. And not even first success rate, right? Because I'm assuming there's not one or two, there's only one large group pooled. So truly just pooled success rate, pooled failure. I'm going to have pooled success rate, pooled failure. And I'm going to divide this by the number of trials. So in this case, 260 number of trials for that evening group, and 140 number of trials for that morning group. And what I said earlier about this being pretty forgiving, if you had this in the opposite order, you would still end up adding the same fractions. So it's okay if your denominators are switched for the setup here. I'm going to type this into a calculator and I'm going to see what I get. I get 0.052. So here's what this means. I anticipate there being no difference in the groups, that they have the same success rates. If there is a difference, I expect that difference to vary by about 5.2% up and down. That's the standard deviation for the differences of the two groups. So I'm going to draw my model, thinking about what this really means. And again, we're going to do more than one example of this. I'm starting with the center of 0, and I'm going up and down by that 5.2%. So I anticipate the null hypothesis claims the two groups are the same. And that might not actually be true. We might see that the first group is way bigger than the second group. I could have a tail coming off on this side. I could see that the second group is way larger than the first group. Maybe I have a tail coming off on this side. So this represents no difference. This side would mean the first group is larger. This side would mean the second group is larger. So I've done my first step. I have my hypotheses. Hypotheses again, I'm assuming no difference. Alternative is second group is larger than the first, or that evening is bigger than morning. I came up with my model. I should check assumptions. I'm going to keep going. I'm on my third step here. I'm calculating the p-value. And as I write down this calculation for the p-value, I'm going to remember that definition. It's going to tell me what to do. The p-value is the likelihood. So the p-value is the probability of some event. It's the likelihood of my sample data. So my sample data will be the true success rate for the evening minus the true success rate for the morning. Looking back at my data, I had 150 out of 260 people go inner tubing in the evening. In contrast, I had 60 out of 140 people go inner tubing in the morning. Now the symbol or more extreme, the p-value is the likelihood of my sample data, or more extreme is the symbol for my alternative hypothesis. So when I shade this thing, I'm going to have it shaded to the right. I'm going to type this number inside of my calculator because this is going to give me my value when I find my z-score here in this next step. So I do 150 over 260 minus 60 out of 140, and this gives me 14.84%. I was expecting a difference of 0, and I got a massive difference of the two groups of almost 15%. So on my curve, this is way out in the boons up here, 0.1484. And the direction I'm supposed to shade, it says or more. I think evening is more than evening. I think that evening is more than morning. So I'm shaded to the right. Since it's shaded to the right, when the time comes, I'm going to do 1 minus the table value. And already I can see this is going to be a really, really small tail. I'm going to have a small p-value. I'm still going to go through the steps like normal. So next thing I'm going to do here is I'm going to find my z-score. And z-score is always and forever my value minus the center of my model divided by my standard deviation. In other words, I experienced a difference of 14.84%. But what I was anticipating was a difference or a center of the curve of 0. I'm going to divide this by what I'm counting by. I was counting by 5.2%. When I do this calculation, I'll see that this is a little bit more than 2, not quite 3 tick marks away. I believe I end up with a z-score of 2.85. Okay, I'm going to look this up on the table. And when I look this up on the table, remember the first 2 digits here are telling me the row. So I'm going to be in the 2.8 row. The last digit tells me the column. So I'm going to find where 2.8 meets the 5. Let's see if I can find that. I have the 5, I have the 2.8, and this is meeting right here at 0.9978. So my table value, if it was shaded to the left, this would be my p-value, is 99.78%. But my picture is not shaded to the left, it's shaded to the right. So whenever it's shaded to the right, to find the p-value, it is 1 minus the table number. 1 minus 99.78 leaves me with a p-value of 0.0022. So first step, hypothesis, second step, model, third step, p-value, fourth step, conclusion. I have a p-value of 0.0022. And if I have an alpha of 5%, then my p-value is low compared to that alpha level. A reminder, 5% is like a nice neutral alpha level. This is when both type 1 and type 2 errors are equally bad. If my p-value is low, the null must go. I must reject the null hypothesis. If I reject the null hypothesis in either one of these situations, that means I have evidence that E minus M is a positive number. Or in other words, I have evidence that the evening group is larger than the morning group. So by rejecting the null hypothesis, I have evidence more people percentage-wise. So not in terms of raw number, but proportionally, go inner tubing in the evening. So in other words, I have evidence that the evening group is larger than the morning group. The downside is a hypothesis doesn't tell me how much more. So I don't know if this is a difference of like 10% more for the evening compared to the morning group, or if it's as low as just 1% more. And if you wanted to know how much more, well, this is no longer a fair or not fair, yes or no type of question. This is a more nuanced, I have multiple values here. This sounds like something that could be answered using a confidence interval. So something that I might encourage you to do is to go back and create a confidence interval for the same set of data here. And what you should notice is your confidence interval should be greater than 0. It's a positive number. It's out here on the side. In other words, your confidence interval should miss that value for 0. It should be a conclusive result. Now that's a lot the first time you're going through it. So I'm going to do another one of these things, just the 4 steps back to back to back, to show you that in practice this goes much faster than it looks. So I'm going to turn the page and we're going to do another one. This one's about water slides. A little bit of a nautical theme apparently. So Jessica Drew is a water slide aficionado. She's also a student of gender studies, and she thinks that there is a gender bias when it comes to certain rides. So to test to see if there's a relationship, she asked people their gender, however they identify. She only got people that identified as male or female. I might question her ability as a gender student study. And if they rode or did not ride the ride high tide. Test the claim that the proportion of males that ride high tide is different than the proportion of females that ride high tide. Use an alpha level of 10%. In other words, she doesn't want to be really sure of this result. She's happy to get by with a low confidence level. So here's what I'm going to do. I'm just going to set up the framework. And I know I'm going to have 4 steps. I know from practice that step 2 is long. So I'm giving myself plenty of room for step 2. First step will be my hypotheses. Second step, model. Third step, p-value. Fourth step, conclusion. Hypotheses, model, p-value, conclusion. Okay. And before I do a lot more than just set up the framework here, I also want to kind of visualize what it would look like if I did not see gender. And if I did not see gender, I'm going to have just an overall number of people that either did the ride or did not do the ride. So adding these 250 and the 390 together, I see that 640 people rode high tide. So if I didn't see gender, that's my number of successes. 640 and 720, so assuming I cannot tell the difference between these two groups, 1,360 did not go on the ride. Adding these together, this is telling me that this is out of 2,000 individuals. These tables have a name. These are called contingency tables. And from this contingency table, I can see my overall success rate. So my pooled success rate, if I cannot tell the difference in gender, 640 people rode the ride out of 2,000. That gives me a success rate of 32%. Now, the individual success rates for male and female might be different. That's what we're testing. For now, I'm assuming that they're the same, and I can just clump it into 32. If 32% rode the ride, that tells me the remaining 1,360 out of 2,000, or 68%, did not ride the ride. Reminder, these two things are opposites or complements of each other. So 32 and 68, this adds up to 100% for me. Tiny bit more prep work. I'm just going to add these numbers together to see what I'm working with for sample sizes. So the number of males that I have for this problem, 890. Number of females for this problem, 1,110. Okay, I've set up the framework. I'm going to go through all the steps now for the problem. Hypotheses, model, p-value, conclusion. First step, hypotheses. I'm going to have you pause the video if you're watching this thing at home. Take a minute or two and see if you can come up with that null and alternative hypothesis before we do it together in the video. Okay, I'm going to assume you paused the video here, and now let's go through it together. So null hypothesis is always going to be that there is no difference in the group, that the percentage of males that go on the ride is the same as the percentage of females. The other way that I could write the same thing is I'm assuming that if I take the male group minus the female group, that I would get 0, that it's the same number. I'm setting it up twice here. You could really set it up with either one of those things as your null hypothesis. And reading through this, it says test if there's a difference. So alternative hypothesis, I'm going to be testing not equals. In other words, I'm going to test male minus female if it's anything other than 0. So this is not going to be a left-tailed or a right-tailed test. It's going to be both. This is going to be a two-tailed test. I'm moving on to step 2. I'm coming up with my model. When I was doing hypothesis test 4, my model looked like p hat was normally distributed with a center of p and a standard deviation of square root pq over n. I'm going to use the same framework here, except I'm doing this twice. So I'm going to have this for one group minus the same thing for the other group. Now, when I'm subtracting this other group here, I can choose the order. So looking at this thing, if I know the male success rate and the female success rate, I might want to do this in the order of male minus female if I think it'll give me a positive number, or maybe female minus male if I think it'll give me a positive number that way instead. So set this up in whichever way you think is convenient. I haven't done any prep work, so I'm just going with this. So I have p hat is normally distributed with the center of p, standard deviation of root pq over n. And then I have the same thing here for the second group. P hat has a center of p and a standard deviation of root pq over n. And when I'm saying p and q, that's my pooled success rate. When I say n, that's the number of males. When I say n, that's the number of females. Well, if I'm assuming the success rate is 32 for both groups, then 32 minus 32 gives me a center of 0 every single time here. There's no difference. That's what's being claimed. For P, I'm plugging in 32. For Q, I'm plugging in 68. For P, 32. For Q, 68. The number of males, I'm wondering how groups of 890 and 1,110 vary assuming that there's no true difference. I'm going to type this result into a calculator and I'll see what I get. I got a standard deviation of about 2.1% or so. So I'm going to move on to the next step, p-value. The p-value is the likelihood, so I'm looking at the probability of something, of the sample data. Well, my sample data is the success rate for the males minus the success rate for the females. So I'm going to go back up to the raw data here. Success rate for the males. Well, 250 wrote it out of number of males, 890. Success rate of males, 250 out of 890. Success rate for females, I had 390 out of number of females, 1,100 and, 720. Nope, 390 out of 1,110. So I have success rate for male minus success rate for female, and I'm testing for a difference, or more extreme in this case means two-tailed. So I'm going to draw my picture. Null hypothesis, no difference. And then I am counting by 0.02 or so in both directions. Now I'm going to find my z-score by taking the value that I get when I do this difference. And when I subtracted these numbers in my calculator earlier, I got negative 0.07. So in hindsight, I probably should have done female minus male, but that's okay. My value is negative 7%. That shows up here. Minus my center is 0. I am counting by 0.021 or 2.1%. This gives me a z-score of negative 3.33. If you're following at home, I'm going to ask that you do two things here. One, I'd like you to finish drawing in this picture. I started this, but shade it in the appropriate direction to shade it. The second thing I want you to do is look up this negative 3.33 in your table and use that to come up with a p-value. Pause the video, give it a go, see what you can come up with. Okay, assuming you pause the video, I have my value out here at negative 0.07. My z-score for this is negative 3.33. And when I'm shading this thing, I might have shaded this thing to the left for this, but be careful. Remember, this is a two-tailed test. So I'm really testing in both directions, two tails. So my z-scores actually have two. One of my z-scores is negative 3.33, and my other z-score is the same thing but positive. So this would be a positive z-score of 3.33. So when I'm saying look up the table value, I'm always going to look up the table value for the left side. That's going to make it a lot easier when it comes time to find that p-value. So inside of my table, I go to negative 3.3. So I'm on the negative side. And I'm going to find where this meets the column for 3. And on mine, it happens right there at 0.0004. This is not my p-value. This is just the size of that left tail. So if I want both tails, I need to do 2 times the left side. So 2 times that 0.0004 actually gives me a p-value of 0.0008 or so. It's still ridiculously small, but I need to make sure I multiply by 2 because sometimes it makes it just large enough that I stop rejecting and I start to fail to reject. Now I'm using an alpha level of 10%. So if I noticed 0.08%, that's extraordinarily small compared to that alpha level. It's a statistically significant result. If the p-value is low, I reject the null hypothesis. The null must go. If I reject the null hypothesis, this must mean I have evidence of the alternative. So I have evidence, ... that the proportion of males and the proportion of females that go on this ride high tide is different. If I want to know, well, which group tends to go on the ride more, actually taking just a quick look at this, I'm noticing that I got a negative number. So it actually looks like females tend to go on this ride more than males. If I want to know how much more, again, that's a question that should be answered using a confidence interval instead of the hypothesis test. Hypothesis test just tells me if something looks fair or not fair. Confidence intervals will clarify as to what exactly that means in context. We're going to do another example of this. Just going through that four-step process. So this is just the same thing again, just one more example. Zach works as a cat suite manager at the Grand Cat Tower Hotel. Fiona's zipping around in the background. She would love to go to a private hotel, I'm sure. Thanks to the proportion of hotels that in the US that allow pets has increased from the years 2014 to 2015. In 2014, he found that 60% of 150 hotels sampled allowed pets. In contrast, in 2015, 83 out of 120 sampled hotels allowed pets. Okay, let's do some calculating. If you're following at home, we're doing the first step, we're doing the hypothesis. Pause the video, see if you can come up with the null and alternative hypothesis. We're trying to test if there's been an increase from the year 2014 to 2015. Let's take a look. So I can set this up either way, but for my null hypothesis, I have that I think the year for 2015 is the same as the year 2014 for my success rates. Alternative hypothesis, I think the 2015 result is larger than my 2014 result. So if I'm going to do the subtraction for the other way of writing these hypotheses, I might want to write down the large number, the 15 result, down first, and then subtract the small number, 14, second. Now, what I'm claiming is that there's no difference between the groups, so we shouldn't get a significant number at all if there's no difference. But should there be a difference, when I do the subtraction, I might end up with a positive number. This is telling me the direction I'm going to shade. I'm going to shade to the right when I'm setting up this problem. Determine the model, including the center and standard deviation. Okay. I've decided that I'm going to do year 15 minus 14. It's going to be normally distributed. My center is always 0. My standard deviation is my success rate times my failure rate, number of samples for the first group, plus success rate, failure rate over number of samples for the second group. I already have the center, so I'm halfway there. I also have the number of samples for each group. In 2015, there were 120 hotels. In 2014, there were 150 hotels. I need my success rate and failure rate if I'm treating these things as one large group. And I need my failure rate if I'm treating this as one large group. If you're following along at home, go ahead and pause the video and try this out. Just a tip as you're trying to do this on your own, be careful with the 60%. 60% is not my value yet. This is a percentage. So you might want to convert the 60% to a count before you try to combine them together. They should both be counts when you're adding the total number of counts on the top of that fraction. So pause the video, give it a go, see what you can come up with. Okay, I'm going to do a tiny bit of scratch work. The number of successes in 2014 is 60%, 0.60, of 150. So if I multiply 60% times that 150, I get 90 hotels in 2014 that I sampled allowed cats. So in total, I had 90 for the first year, and I had 83 for the second year. I sampled 150 hotels in the first year. I sampled 120 hotels in the second year. I'm going to type this into my calculator, and I'm going to see what I get for that pooled success rate. And then whatever I get, I'm just going to do 1 minus to get my failure rate. So I have 173 divided by, looks like 270. I get 0.641 approximately, so I'm going to make those little wiggly signs. 64.1% is my success rate, so that means my failure rate, 1 minus this, should be about 35.9%. So I'm going to add that. My P is 64.1, my Q is 35.9, my P is 64.1, a little bit small and hard to read, but I'm just taking these numbers and I'm plugging them in. My Q is 35.9. I'd like you to type that standard deviation into your calculator there. I'm plugging in this as my P and this as my Q. Let's see what we get. When I did this in my calculator, I got something like 0.0588. 3 digits, probably at least a good idea. I'm using 4 here. I'm just being a little bit more cautious than normal. Calculate the p-value. So reminder, p-value is the likelihood of my sample data, and I have 2 sample data here, or more extreme will mean more in this case. I decided for the order of subtraction that I wanted to do the year 15 minus the year 14. In 2015, my success rate was 83 out of 120 hotels. In 2014, my success rate was 60%. I don't have to do the division, but if you wanted to, the division there would look like 90 divided by 150. I'm going to type that 83 out of 120 minus that 0.6 into my calculator just to see what I'm working with for my value. When I'm drawing the curve, I ended up with 0.0917 or so. Actually ended with 0.09166 repeating, so I could have written the 6 with the bar above it. So I'm going to draw my curve. In the center of the curve, I was expecting a difference of 0, counting by about 0.588 or so. I noticed a difference, more than 1 tick mark, less than 2, so I'll probably have a z-score of 1 point something, of 0.0917, or more extreme, so I'm going to shade this thing to the right. So I'm going to be looking at that little tail there. I'm going to find the z-score the same way I always find the z-score, by taking my value minus the center divided by the standard deviation. My center is just subtracting 0, so I have to do almost nothing on the top. I just take whatever my difference was before, So on the top, I have 9.17%, divided by, I am counting by my standard deviation. My standard deviation is 5.88%. When I do the division here, I get approximately 1.56 as my z-score. I'm going to look that up in my table. I'm in the 1.5 row in the 6th column. If you're doing this at home, please find that table value and then also calculate the p-value. Be careful about the direction when you find your p-value. If you're feeling brave and confident about that, go ahead and see if you can come up with a conclusion. Let's suppose you use an alpha level of 5%. I'm going to go through this. 1.5 meets the 6. I'm looking at a table value of 94.06%. I notice that my picture here is shaded to the right, so I want 1 minus the table value to get my p-value. 1 minus this gives me 0.0594 or so. My alpha level was 5%. This is actually larger than 5%. So since my p-value is bigger than my alpha, I fail to reject the null hypothesis. In other words, I'm stuck between these two things, thinking there's probably not been an increase or not been a change in that rate from 2014 to 2015 in a meaningful way. I do not have evidence of an increase in cat-friendly hotels from 2014 to 2015. So were I to follow this thing up with a confidence interval, I should notice that that interval includes 0, that there's no discernible difference between the two groups. I'm going to quickly look at that confidence interval with you, taking my sample rate for 2015 minus the sample rate for 2014, plus or minus my z star. And then I have my sample info for 15, my sample info for 14, and I'm combining the two pieces together. So when I created this model, I assumed the two groups were the same, so I plugged in the same success rate here. When I am doing my confidence interval, I don't make that assumption. So where it says 2015, I will plug in my 2015 success rate. Where it says 2014, I will plug in my 2014 success rate. So it might help to do a little bit of scratch work on the side. My success rate for 2015 was 83 out of 120 hotels. That as a decimal was 69.2% or so. So my failure rate for 2015 is 1 minus this number. That gives me 30.8%. Number of samples for 2015, I was rocking 120 samples. For 2014, this is considerably easier because they give me a percentage already. It says 60% due. So then my failure rate for 2014 is 40%. And this is out of 150 hotels. If you're following along at home, pause the video and see if you can figure out this next bit. I did a one-tailed test with an alpha of 5%. What should my confidence level be for the area in the center? So a reminder, the picture of what's going on here. I'm assuming I have 5% in one of the tails. Now, I shaded the tail to the right earlier, so I'll be consistent. How much area does that leave me with for the center? So pause if you're doing this at home, find C, and then what is the critical value for that C level? Okay, if I have 5% here, I also have 5% here. That leaves me with 90% in the center. If I have 90% in the center, my critical value of my Z star for that result was 1.645. I'm going to plug in my numbers. 2015, my success rate was 69.2 minus 2014, my success rate was 60. So I'm taking my confidence interval formula, 1.645, square root 69.2, 30.8 over 120. So there's my confidence interval for just the year 2015. And I'm going to do this again here for the year 2014. So I have 60%, I have 40%, and I have 150 samples. I subtract the centers. I'm looking at the difference. I'm adding the spread. I'm typing this into my calculator once with the plus and once with the minus. And a reminder, in the last problem, I failed to reject the null hypothesis. So when I do this, I think I'm probably going to have an inconclusive result. An inconclusive result happens when you have both a positive and a negative inside of your confidence interval. So when I did this thing for the low end, I got negative 0.004 or so. It's still a negative. Do you see how this 0.0594 was actually really close to this? So I just barely failed to reject the null hypothesis. I just barely include a negative number here. On the high side, I'm going to do this with the plus. Changing this minus to a plus gives me a high value of 0.188 or so. So 0 is in our interval because I have a negative and a positive. So this tells me that perhaps it's possible that my success rate for 2014 is the same as my success rate for 2015. In other words, I think my results here are inconclusive. I do not have evidence of an increase from the year 2014 to the year 2015. We've now seen several examples of this hypothesis test for two proportions. Each time I'm using pooling. Last lesson and also one time this lesson we did confidence intervals. When I do confidence intervals, I still have each of my unique probabilities here. So just as a general reminder, I only have to pool when I assume my two groups are the same. And I'm only assuming they're the same when I have an equals 0 in the null hypothesis. So only pool for this two proportion hypothesis test. If you're following along in the 5-page packet of notes, you should have an example of 5 problems here. This says confidence intervals. Do the confidence intervals, but also do with a hypothesis test. And see if you can determine a difference between the two groups, testing that does not equals for each. And whatever your results are for your hypothesis test, they should match up to your results for a confidence interval. We've now looked at one proportion at a time, testing claims and coming up with intervals of possible values. We've looked at 2 proportions, comparing one group to another group. What we've not done yet is compared like 6 proportions at the same time. So for example, I've not compared the pass rates for 111, 95, and 60 all at the same time. Currently, I can only compare 111 to 95, 111 to 60, 95 to 60. That feels really, really labor intensive. So we have done a lot with proportions so far, but we will return to this in several lessons. So later, we will learn how to compare 3 or more groups. And the interesting thing is when we learn how to compare 3 or more groups, this is going to be something called chi-squared. Chi-squared will still work for comparing 2 groups, but it's strictly a test. It's just going to tell me if something is fair or not fair. Whenever I want to know how something is fair or how something is unfair, I always have to return to this confidence interval thing. So of the 2 lessons, lesson 4 and lesson 5, I would say that lesson 4 is considerably more important. Confidence intervals in general just have way more weight to them than dealing with hypothesis tests. That's it for now. We're going to make a transition to looking at averages for a while. Your first exam is on nothing but proportions though, so lessons 1 through 5 is what you should expect for that first test. See you for now.